Hello, and welcome to the next lesson in the Waves unit. In this one we're going to be having a look at the EM spectrum. Outcomes from this lesson: you need to be able to organise the radiations of the EM spectrum in order of wavelength and frequency. You need to be able to give applications or uses for each of the radiations. You need to be able to state a detector for each of the radiations as well. You need to be able to state that all radiations travel at the speed of light, or 3 times 10 to the power of 8 meters per second. You also need to be aware that all radiations from the EM spectrum travel as transverse waves. So firstly, what does the EM spectrum stand for? The EM spectrum stands for the electromagnetic spectrum. The EM spectrum is a list of all the electromagnetic waves. Another way of saying this is that it's a list of all the types of light. Because all the radiations in the EM spectrum can be thought of as forms of light, they all travel at 3 times 10 to the power of 8 meters per second. Here's a diagram of the electromagnetic spectrum. Electromagnetic radiations, or these forms of light, go from radio waves to gamma rays. TV waves are also a form of radio waves, so you often see radio and TV waves grouped together. On the bottom of the diagram is a rough guide to the wavelength of each of these different emissions. Radio waves are by far the largest. Radio waves can have a wavelength of several kilometres. At the other end of the spectrum, gamma rays are exceptionally small. The visible light spectrum is right slap bang in the middle of the EM spectrum. As a rough guide, the larger waves tend to be used for communication purposes, so radio waves, microwaves and infrared can be used for long and short range communication. On the other hand, the smaller waves like ultraviolet, X-rays and gamma rays tend to have medical uses. However, there are several uses for each of these emissions. In order of decreasing wavelength, radio waves are the largest, microwaves the second largest. Infrared radiation are smaller than that. In terms of their wavelength, the EM spectrum can go from radio waves, which have the largest wavelength, all the way down to gamma, which have a tiny wavelength. However, as the wavelength decreases, the frequency of these waves increases. This is because of the wave equation, or V equals F lambda. Because the speed is a constant, all these waves travel at the speed of light. As the frequency increases, in order to keep the speed constant, the wavelength must decrease. So what are these electromagnetic waves? That's a bit beyond what you need to know for a National 5 exam, but I'll give you a rough description. Electromagnetic waves are made of an electric field and a magnetic field. The electric and magnetic fields vary, and the Scottish physicist James Clerk Maxwell found that if you vary one, it must produce the other. These changing electric and magnetic fields mean that electromagnetic radiations don't need any material to travel through. This is why we can get light from the sun travelling through the vacuum of space. James Clerk Maxwell predicted the electromagnetic spectrum in the 1860s. He produced a series of equations that show how magnetic fields and electric fields interact with each other. He showed that they should produce electromagnetic waves that would travel at 3 times 10 to the power of 8 meters per second. At the time he noticed that this was eerily similar to the speed of light, and he thought it was too much of a coincidence that light should travel at that speed, and that these electromagnetic waves would also travel at that speed. He therefore concluded that light was an electromagnetic wave. So now we'll have a look at each of the emissions in a bit more detail, starting with radio waves. Around 20 years after Maxwell's discoveries, German physicist Heinrich Hertz produced the first radio waves. Initially they were called Hertzian waves. Nowadays we know that radio waves can be used for long-range communication, but at the time Hertz thought that there was absolutely no application at all to these waves. It wasn't until after Hertz that Marconi produced the first commercially viable long-range radio technology, and so he's often credited as being the inventor of the radio. Marconi's inventions became so successful that eventually ships had to carry a radio. When the Titanic sank in 1912, the radio operators sent a distress signal and a nearby ship called the Carpathia arrived to rescue some of the passengers. After the Titanic disaster, Marconi's invention was proclaimed a huge success. Radio waves are usually produced by electronic circuits, but radio waves can also be produced by generating sparks, and so radio waves are often produced in lightning storms. And in my physics classes, radio waves are generated by a Van de Graaff generator. Radio waves are detected by aerials. The waves are very large, typically with a wavelength of a couple of kilometres. Radio and TV waves can be used for long-range communication. Next we'll have a look at microwaves. Now normally when students think of microwaves, they think of a white box that you put food in and it heats your food up. That's a microwave oven, and it uses microwaves to heat food. The microwaves themselves are really a form of light, an electromagnetic radiation. Again, microwaves are usually produced by electronic circuits. Again, microwaves, like radio waves, can be detected by aerials. But microwaves are a lot smaller than radio waves, typically being a few centimetres long. As well as being used to heat water and food, microwaves are used for long-range communication, including Wi-Fi signals. Infrared radiation was discovered by William Herschel. William Herschel conducted an experiment. He was trying to find out how much heat energy was transmitted by light, and so he conducted an experiment using a blackened thermometer. He took white light, passed it through a prism, and this white light refracted into the visible spectrum. He then used the thermometer to measure any temperature changes across the visible spectrum. It was only when he set his thermometer down, beyond the red, that he noticed a large temperature increase. He then correctly reasoned that there were electromagnetic waves beyond the red that couldn't be seen by the naked eye that transmitted heat. And really this is what infrared is. Infrared transmits heat energy from hot or warm objects. We could use a blackened thermometer like Herschel did to detect infrared, but electronic devices like photodiodes or even heat-sensitive paper can be used. Infrared waves are very small, around the size of a grain of sand. They're used for short-range communication, like Bluetooth or in a TV remote. Because infrared transmits heat energy, it makes it useful. They can be used to build thermograms or heat pictures from any object. These can be useful for night vision goggles. Thermograms would also allow engineers to detect heat losses in buildings, so that homeowners or business owners can find out how to best insulate their buildings. Visible light. The wavelength of visible light goes from violet to red if we're going from the shortest wavelength to the longest. The wavelength of visible light is typically around 400 to 700 nanometers. Visible light is produced by bulbs or LEDs, lasers, the sun. They're detected by cells on the retina of the eye or a photographic film. The waves are very small, about the length of a bacterial cell. Invisible light can be used in lasers, and again, for communication purposes through optical fibres. Ultraviolet, produced by special lamps, by the sun, can be detected by photographic films or fluorescent materials. The image shows a child's hands covered with a fluorescent paint. Many people mistakenly think that they can see ultraviolet because of this effect. In reality, the paint absorbs the ultraviolet and gives out visible light. The waves are tiny, about the length of a molecule. And ultraviolet has a few uses. Banknotes and identification cards have holograms that can be seen under ultraviolet light. Ultraviolet can be used in the forensic sciences to detect bodily fluids. But ultraviolet can also be dangerous to living things, and so it can kill bacteria during water treatment or food production. Obviously it's the UV from the sun that gives us a suntan, and so UV is used in sunbeds. Because of its short wavelength and its high frequency, it means that ultraviolet rays are very high energy. Ultraviolet's a form of ionizing radiation, and so it can cause cancer and sunburn. X-rays. X-rays are produced at very high energies and can be detected by photographic films. The waves are even smaller, about the length of an atom. And obviously X-rays are used to see what's happening inside the human body, detecting broken bones and the likes. But out with medical uses, they can also be used in airport security. So when you put your bag into security, it goes through an X-ray machine to detect anything that might be dangerous inside the bag. X-rays again are very, very high energy and so can kill living tissue and cause cancers in high doses. That's why when you go for an X-ray, the staff will disappear into a separate room, because constant exposure to X-rays could be dangerous to their health. And lastly, gamma rays. Gamma rays are produced by radioactive decay or nuclear reactions. They can be detected by a photographic film, but more commonly detected using a Geiger-Müller tube. The waves are the smallest of the EM radiations, about the length of an atomic nuclei. And gamma is used in medical treatments, such as radioactive tracers and radiotherapy for cancer treatment. Because gamma can kill living things, it's used to sterilise medical equipment. Because gamma transmits more energy than any of the other types of radiations from the EM spectrum, they can be dangerous. They can cause cancers and kill healthy cells. So the last thing I'd like to do is have a look at a couple of past paper examples to give you an idea of the sort of questions that you could be asked. With this one here, it's a pretty typical question. It will give you a section of the EM spectrum and normally one or two will be missing. Here we see gamma rays, an unidentified emission labelled R, then ultraviolet, then visible light. The question asks which row in the table identifies radiation R and describes its frequency. At this point, pause the video, see if you can find the answer. So radiation R is in between ultraviolet and gamma rays. That would be X-rays. In terms of the frequency, remember that gamma rays are the highest frequency, and from the diagram we see that R has a larger wavelength than gamma rays. And remember, when the wavelength increases, the frequency must decrease. So how does R relate to the visible light? Well, R obviously has a lower wavelength than visible light, and therefore it must have a higher frequency than visible light. So we have X-rays that have a higher frequency than visible light. That would be answer A. The next question. Can you state a detector of infrared radiation? Pause the video, have a think. So remember, infrared radiation can be detected by a photodiode, a blackened thermometer, or heat-sensitive paper. The next question asks, state which radiation in the EM spectrum has a wavelength shorter than X-rays. Again, pause the video, have a think. The only radiation in the EM spectrum with a wavelength shorter than X-rays is gamma. The next question requires you to do a little calculation. An electromagnetic wave has a frequency of 1.2 GHz, that's 1.2 times 10 to the 9 Hz. Show that the wavelength of this wave is 0.25 meters. Pause the video and see if you can do this calculation. So this question needs us to use V equals F lambda, and a lot of pupils forget that all electromagnetic waves travel at the speed of light, so even though it doesn't explicitly give you a speed, we do know that it's an electromagnetic wave, and so 3 times 10 to the power of 8 meters per second is the speed. Using that information, we can use lambda equals V over F, which is 3 times 10 to the power of 8 divided by the 1.2 GHz, and that indeed gives us 0.25 meters. As a side note, for these show questions you have to start with the equation. You get the 2 marks, one for using the equation and the second one for putting the numbers in the correct place. That's why it's only worth 2 marks and not 3. It already gives you the answer. Lastly, identify the part of the spectrum that this wave belongs to. Remember that the wavelength is 0.25 meters, so pause the video and have a think about whether or not this wave would be a microwave, an infrared, a visible light, ultraviolet or X-ray. So another way to say 0.25 meters is 2.5 times 10 to the negative 1 meters. If we see the wavelength scale along the bottom of the diagram, times 10 to the negative 1 would put it somewhere in the microwave region. So the answer would be microwaves. So, the outcomes of this video. You need to be able to organise the radiations of the EM spectrum in order of wavelength or frequency from large to small and backward. Give an application or two for each of the radiations. State a detector for each of the radiations. Please remember that all radiations travel at the speed of light, so if you're given a calculation involving a member of the EM spectrum, remember you always have the speed, 3 times 10 to the power of 8 meters per second. And lastly, all radiations travel as transverse waves. It's just these constantly changing electric and magnetic fields. So I hope you found this video useful, and thanks for taking the time to watch it. Please like and subscribe. I'll catch you later.